All right, so it's right at the hour, and welcome everyone to our C2QA Quantum Co-Design Center for Quantum Advantage Summer School on a practical guide to building superconducting qubits. And this is an 8-lecture series, and this is the second lecture of the 8. So last lecture on Monday, you heard from Steve Gervin giving you a basic introduction of what is a superconducting qubit and the basic concepts in this field. So today we are glad to have Professor Jens Koch with us. And Jens is a professor in Northwestern University, and he is known as the person who has introduced the transmon to the world. Yeah, so you learned about transmon, and so today you're going to hear in more detail of how do you actually design a qubit, and how do you model and understand and to translate your electrical circuits into this quantum Hamiltonian that we all love and use. Okay, so the stage is yours, Jens. Everyone, you can type in questions in the Q&A session, and we'll either answer it in text or we will group questions and address live in the session. Okay, Jens.
Okay, and they're little icons floating over my screen. This is lovely. Thank you, Jen. It's great to be here. And so, yes, I will try in the time that I have to give a tutorial to circuit quantization. Time is limited, so I don't think we'll cover everything that we know about circuit quantization comprehensively, but I'll try to do a good job to get you started and give you a flavor of what's involved, and also give you an introduction to some of the tools that are around that actually allow us not to do circuit quantization by hand each and every time these days. All right. So indeed, lecture overview for that reason is like this. The plan is, imagine you have some circuit. The circuits that we will look at are going to be quite simple, and we'll study a little bit how to do circuit quantization by hand. It is a systematic procedure, but it tends to be tedious. Usually if it's anything but a harmonic oscillator, in the end, you will be forced to do some numerics, most likely. So computers our classical computers are going to be involved anyways. Last but not least, towards the last part of the tutorial, I will talk a bit about SC qubits, which is a Python package that my group and I have released a little while ago, which now also allows you to do automatic quantization of circuits. So we'll talk a little bit about that. Good. So here's the roadmap, right? You start with some circuit that might be of interest to you. It could be the one that is down there, which is the 0 pi circuit. Could be something simpler or more complicated. And then there's some road, and at the end, what you probably are interested in are things like what is the energy spectrum of that circuit, what are matrix elements that govern the coupling of that circuit to other circuits, things like that. And my little animation is just slightly broken because the classical Hamiltonian is sort of sticking already out in the middle of the road. That's one of the pieces where that they will visit as part of that journey. We'll formulate a Lagrangian for that circuit, then perform a Legendre transform, get a classical Hamiltonian, quantize that, get a Hamiltonian matrix, and that ultimately is what allows us to get all of the static properties of the qubit, which then also get fed forward into time evolution simulation if you want to simulate a gate fidelity, for instance. The real references for learning circuit quantization by hand systematically, there are 3 that I like that are down there for you to visit and read, but I'll move on here in my own fashion. The circuit elements that I will focus on are these 3 here: capacitances, inductances, Josephson junctions. Those are indeed the main 3 ones. There are some people who are investigating more exotic things like quantum phase slip junctions, but we'll deal with just these 3. they can be made out of superconducting material and are dissipationless, which is one of the things that we know and like about them, so that our qubits ultimately have decent T1s. Now, when we say circuit quantization, the truth is that everything sort of starts on the classical side. And indeed, most of the work that you have to do for circuit quantization happens on the classical side when we have to ask ourselves, well, what variables do we want to use to describe the equations of motion of that circuit? What kind of equations do we get? Can they be represented as a Lagrangian, which is maybe not the typical thing that you've learned in classical mechanics, where perhaps your systems were actually mechanical rather than electric. And so an important starting point for circuits are Kirchhoff's laws. You know them. There's the current law, which says that if you sum up the currents coming into a node of the circuit, then that total current has to equal the outgoing current. That's what's expressed down here. And then the Kirchhoff's voltage law says if you have any loop in your circuit, then summing up the voltages going around, perhaps if needed, including an EMF voltage, we'll get to that later, those voltages have to sum up to 0. And so if you take these two, the current law, the voltage law, and you combine that with constitutive relations that we'll revisit in just a moment, as well as simple truths like the time derivative of charge corresponds to current, then we get to formulate both constraints as well as equations of motion, which we can then rephrase in terms of the Lagrangian and then obtain from Euler-Lagrange equations. So we'll get there. The two circuit elements that we start with are the ones that you already know and love, I hope. So capacitances, inductances, here are their symbols. The constitutive relations are such that there's always something here. I've arranged this so that on the left-hand side, there's a charge-related quantity. So charge is capacitance times voltage across the capacitor. And here for the inductor, its current is flux divided by the inductance. So on the left side, again, they're charge-like variables, right? Current is Q dot, if you wish. And on the right-hand side, it's voltage or flux. I'll say a little bit more about the relation between flux and voltage in a moment. The energy can be written down in two equivalent forms. So for the capacitance, using charge-like variables, you would say, well, the capacitor stores an energy that is Q squared over 2C. Equally, you could say it's 1/2 C V squared, with V being the voltage. And then for the inductor, you've seen similar expressions with energy being expressed as 1/2 L times the current squared, or the flux squared divided by 2L. And so right now, they're just these two equivalent forms, and we'll talk a little bit about how for a harmonic oscillator, you're welcome to use either form. As soon as we include Josephson junctions, we'll probably opt for one version rather than the other. And I mentioned that here on the right-hand side, I wanted to speak of voltage-like or flux-like variables. Remember from Faraday's law here, modulo the minus sign, that indeed the time derivative of a flux has dimensions of voltage. And so it's useful in this context, since in the constitutive relation for inductance, it's actually a flux that appears, to introduce just generally a flux variable, which even if you don't have an inductance, we can integrate a voltage drop over time from some reference time T0 to the current time T, and that quantity then defines a generalized flux variable. It doesn't have to be a magnetic flux through an inductor. We would equally speak about a generalized flux associated with a capacitance, which indeed then is just the time integral of the voltage across. Okay. And so I'm now rearranging things a little bit using those variables. So you see that I is now replaced by Q dot. Likewise, V is replaced by phi dot, so that things are now systematic in the constitutive relation as well as in the energy. It's charge-based variables or flux-based variables. Good. And so I thought a little bit about what might be a good example. And initially I thought, well, the LC oscillator, you've seen it before, but I think a little bit redundancy is not bad. So there will be some repetition and some will hopefully be new and kind of illustrate to some of you perhaps for the first time how to do circuit quantization in a very simple setting in a place where you still have intuition and there's no mystery involved. Okay. So what I'll do is I'll denote my voltage and current through each of these two elements by V1, I1, V2, I2, right? This is a circuit branch. There are two of them. And of course, Kirchhoff's laws tell us that if I go around the loop like such, the two voltages have to add up to 0, and current 1 and current 2 must be identical. And then just...
Yes, can I just quickly interrupt? So and I thought I know the answer, but just to make sure, someone was wondering whether you are writing on the screen at all, or there's no...
Whether I'll be also writing on the screen?
Or whether you will be writing on the screen.
Maybe in between. I do have a pen just in case, but a lot I've prepared. Is there... I'm curious about the background of the question. Is that a preference?
Oh, no, it's a question of whether you were writing something that they couldn't see for technical reasons or not. I guess the answer is no. Yeah. Okay,
well, let me make sure that I see what you see. Right now on my screen, I see LC oscillator, a circuit, and 2 lines of equations.
Mm-hmm.
Okay, yeah. Then I think we're in sync. Okay. Yeah. Good.
Yeah, thanks.
Now, I'm just rewriting these two relations that we obtained from Kirchhoff's law in terms of our flux-based variables, right? So phi1 dot is V1. So I've rearranged this one. I've rewritten this in terms of Q dots. And now I have two ways to go. Number one, I can start from my relation from the Kirchhoff's voltage law, and I can remember that phi1, which is the flux through this inductance, is L times I1, and I'll then take the time derivative and write this as phi1 dot is L times the second time derivative of Q1. And for phi2, which is the generalized flux variable associated with this capacitance, I'll remember that its time derivative is the voltage across, and that's charge divided by capacitance. All right. And so if I take all of these things together, reminding myself one more time that Q1 dot and Q2 dot are the same, then I get a simple relation that says L Q1 double dot, second time derivative of charge times inductance is minus Q1 over C. So that gives me a second order.
Sorry, just another interruption. Maybe it's good to slow down a little bit, so to address a couple of questions. So
of course,
one question was I thought, because let's clarify this. One is, where is the phi1 and the phi2 measured?
Mm-hmm. So yeah. So phi1 and phi2, they belong to V1 and V2, right? And I'm trying to denote here with this arrow that those are voltages across the elements that they're adjacent to, right? So V1 is the voltage across this inductance, V2 is the voltage across this capacitance.
Maybe just remind the relation between V and the phi. So you answer.
Yeah, let me go back for that one moment. So our generalized flux variables are always such that the flux variable is just the time integral of that voltage, which means that if you take the time derivative, this is now calculus 101 maybe, phi dot is V, right? That's the relation. And of course, for capacitance, there's more to be said through the constitutive relation. We can then relate phi dot to Q over C.
Yeah, there is another question asking what is the current through the capacitor? I guess the underlying puzzle is that electrons don't really flow through the capacitor. So what is?
Oh yeah, but you can shift charges onto and off of a capacitor, right? That doesn't mean that the charges have to go through the insulator, but as you shift charges onto the capacitor, right? You shift charges onto, say, in this onto the right plate and off of the left plate, and that is a net current.
Okay, thanks.
All right, so we have just arrived at our first equation of motion. This is second order differential equation for the charge. And of course, you see what the result will be. Not surprisingly, this will give rise to sinusoidal oscillatory behavior. Now, interestingly, I have a choice. I could have also started with this relation instead. So I went through that exercise as well. So now I'm replacing Q1 dot by phi1 over L, right? This is, again, just constitutive relation rewritten. Phi is L times I, phi is L times Q1 dot. That's what I'm writing for the inductor. And then for Q2 dot, I remember that Q2 is C times V2. If I take the time derivative of that and remember that phi dot is V, then I obtain Q2 dot is C phi 2 double dot. All right. And so now I can plug back in and I get another second order equation of motion, this time expressed in my flux-based variables, but it's the same kind of equation of motion, right? It's the second derivative of phi is -1 over LC if I bring the C over to the other side times phi1. And again, I'll get oscillatory sinusoidal solutions from that. Great. So in this case, for an LC oscillator, having this choice, picking one type of variable versus the other, led us to two very similar looking equations of motion. It turns out that this freedom is diminished once we include Josephson junctions. As soon as we do, and we'll do that in a moment, it's flux variables that are easier to handle and are preferred over charge variables. So whenever you see the Hamiltonian of a transmon, for instance, with at least on the classical side, before you do anything quantum, you'll see a Hamiltonian function that is most likely expressed in terms of a flux variable or a phase variable as opposed to a charge variable. Okay. And then just to finish this example before we talk about Josephson junctions, this is how maybe you derived equations of motion for the LC oscillator a long time ago in some introductory class. And maybe what you didn't think about back then was the fact that these equations of motion are so nice that it looks tempting to ask, can we also derive those equations of motion from a Lagrangian? So let's just try. Lagrangian, our attempt should be, let's write kinetic energy minus potential energy. Here, just still arbitrary, but I'm going to work with flux variables where it's the capacitive term that looks like a kinetic energy term, right? Phi1 is my variable, which now appears here with a time derivative. So that's a generalized velocity, 1/2 c phi1 dot squared. It's like a little bit like 1/2 mv squared or x dot squared for a particle. That's my kinetic energy term. And then I have to subtract the potential energy term, which comes from the inductive energy. So that's phi1 squared divided by 2L. And now, well, let's just try, right? We might remember what the Euler-Lagrange equations are. We take a partial derivative of L with respect to the velocity, the time derivative of that, and then we subtract the partial derivative with respect to the generalized variable. And well, what you will find in this simple case is written here on the right-hand side. And again, that's just yet another form for the very same ODE that we obtained above. So this is success. We can obtain that equation of motion through this Lagrange. Great. And with that established, the idea of how to switch over to the quantum side is relatively straightforward. So most of the work has been done at this point. And then it's just a matter of going through the motions, and you will switch to a Hamiltonian function by performing a Legendre transform. So first we'll find the canonical momentum that belongs to our flux variable. So we'll take the partial derivative of the Lagrangian with respect to phi dot. That is C phi dot. And forgive me, but since notation doesn't really require us distinguishing between 1 and 2, I've dropped that subscript here. So that's why subscript 1 has now vanished. And so C phi dot, of course, you recognize as a charge. It's indeed the charge across the capacitor plates. And that now enters, and I decided to forget a subscript phi. This was supposed to be Q sub phi to remind me that this is the canonical momentum belonging to variable phi. And so this enters the Legendre transform. We do that in the regular fashion. And as our classical Hamiltonian, we get this expression, which is now a quadratic form for the kinetic energy. And then for harmonic oscillator, the potential is also quadratic. So it's Q squared divided by 2C plus phi squared over 2L. And then the simple quantization step is just, it's half a joke and half not. You just put hats on things, right? So your position and momentum now become operators that have a canonical commutator of IH bar. Alternatively, and sometimes more simple is to just remember that the momentum is h bar over I, or minus I times h bar d by d, and then our position variable here is phi.
Yes,
and that leads us.
Sorry, an interruption.
No, that's fine.
To clarify on which term is kinetic energy and which term is potential energy, how do you decide that? And another question is how to understand kinetic energy of the capacitor. Is it a mathematical analogy, or is it, or is there anything that is more fundamental?
Well, I would say I decided on the previous slide to use flux variables. That was a decision. For the harmonic oscillator, I still had the freedom to pursue with a charge variable, but I decided to do this with flux, which means that I have decided that my generalized coordinate is phi, or phi 1, as it is still written here. So that was a decision, right? My coordinate is now phi 1. It's not a spatial position, but that's okay. Classical mechanics doesn't require anything to be a spatial distance, right? You can have angular variables if you talk about the pendulum, all kinds of things where the coordinate in question does not need to have dimensions of length. And once you've selected your coordinate, then it's clear that the other thing with a dot on top is the generalized velocity, right? And so your potential energy term is the one that depends on position, so it's quote unquote our generalized coordinate. And the kinetic energy term is the one that must involve the velocities, right?
Okay, so this may is the reason we can adopt this formalism for quantizing circuits, that the charge and flux turn out to fulfill the requirements of being a conjugate pair. So is this just a lucky coincidence, or is there some underlying principle that lead to this convenience?
So the only thing that we had to check is whether or not the kinds of equations of motion that we get are compatible with Lagrangian formalism. Right? In principle, we could cook up some crazy equation of motion that does not follow from an Euler-Lagrange equation. But we explicitly check that this is possible, and from then on, everything is automatic. There's no coincidence. We really follow the formalism in its purest form. Right? There's our coordinate. There's the velocity. This is how the canonical momentum is defined. I compute it. I recognize that it corresponds to the charge. Even if you hadn't recognized it and given it a different name, it's still your canonical momentum, and it is the thing that on the Hamiltonian side then at first goes into the Poisson bracket, but upon quantization is the thing that, together with the generalized coordinate, forms this canonical commutator. So no coincidence, no luck involved from that point on.
Okay, yeah, thank you.
Mm-hmm. All right. Now, time for the Josephson junction to enter. My understanding is that Steve Gervin already told you some about the Josephson effect and the Josephson junction, and so I will not dwell on this for a long time. The constitutive relation that on one hand has a charge-like quantity on the left-hand side is the current through the junction I, and then on the right-hand side, we said that those are flux-based variables. Doesn't look immediately like this because this phi, lowercase phi, is actually the phase difference where I'm talking about the phases of the two superconductors on the two sides of the junction. That phase difference is this phi, and so you could ask, well, how does that relate to flux or voltage? And actually, Mr. Josephson says, well, this is one of my two. Me being now Josephson, so quote unquote, this is one of my two Josephson relations. This is the second one, which is the phase evolution equation, which says that the time derivative of that phase is actually given by voltage times some fundamental constant. Phi naught here is the superconducting flux quantum, and so again, you recognize that there's a voltage involved, and so we can certainly relate this now to a flux-based variable again, which I think I did here. Yeah, so I'm rewriting this on the next slide. Fine. The energy associated with a junction depends also on the phase difference. Despite the fact that I'm not deriving this here, I didn't ask whether Steve already taught this, but it's a fun exercise where, if you remember how to derive that this here is the energy associated with the flux through an inductor, then the very same kind of calculation is going to give you the minus EJ cosine phi if you start from this different constitutive relation for the Josephson junction. So that's fine. And then the problem that we face is we could ask, okay, we had this column here where energy is expressed in charge-based or current variables. And not only is this relation here nonlinear, the real problem with it is that it's not invertible over the full range of phi, right? So cosine phi.
Yes, are you there? Yeah, to the folks in the audience, it seems like it's Yan's problem on his side. Let me try to reach out to him and see if we can get him to join back. Yeah, so he's on his way back. Just to be patient, maybe a minute or so. Yeah, sorry guys for the drop. Jens is traveling at a conference, so probably that's why the internet was not completely stable. Hopefully he will be back pretty soon, so just hang on for a minute.
Hey, Jin.
Hey Michael, you're using your computer.
I know we're still live and recording, but I'm just logging mine in. He's logging back in now, but we'll have mine as a secondary computer in case it happens again, because I think his whole computer went down, just not the internet.
No,
Sorry.
internet.
Sorry, audience members. We will be back to that sweet quantum in just a moment.
Yep. Sorry, don't say it.
Jen, can you say something real quick?
Okay.
Hi, Jens.
All right. Let me mute myself. Okay. All right. I am terribly sorry for this. I am unsure what caused this. I hope it doesn't take place again. Let me get my slides back.
Okay, yeah. So Jens, you will be you should answer this question before you proceed. What is your favorite qubit? Just as the answer to this interruption.
Well, I think this is a moving target. I think for a long time I like trans ones quite a bit, but there's a lot of interest in fluxonium these days, and it's from the theory perspective, it's a very fun qubit. Michael Hadridge is right next to me, proclaimed earlier that fluxonia are a headache to work with, and that must be on the experimental side, because in theory they're great. But Chen, you can also answer that question. Actually, you have a lot of experience with fluxonium.
I like fluxonium.
Good.
Good.
Very
well,
good.
I think I think a trans bond is still the best behaving child of the of this field, though, right? Yeah. Others could be a little bit strong tempered.
There's something strange now, because
okay. So
I'm unable to share my screen at this point.
We need to make you a co-host, and then you can share.
Okay.
Yeah. Okay. Should be good to go. Yeah.
Okay.
All right, everybody, sit tight. We're back.
Yeah. And again, my apologies. This is the worst disruption I've had forever. Like even COVID was nicer to me as far as that is concerned. Okay, so back we are. And Chen, you tell me how to manage time. This I lost basically 5 minutes roughly, I guess. And we'll manage that.
Yeah,
somehow.
I believe you are at this page. So yeah.
Okay, so the expression that I wanted to briefly mention as problematic was this one, and I can switch back to my laser pointer here if that's better, where we could ask, can we express the energy associated with a Josephson junction in terms of current or charge instead of flux? And there's a problem with that arises from the fact that cosine cannot be inverted over the full range from 0 to 2 pi. And so you end up with something that looks funny. There's a minus or plus. You would have to make a choice. And half of the time you're probably wrong. And so sticking that inside a Lagrangian is not particularly attractive. I'm not saying that it's impossible, that there are things that you can play with, but it certainly doesn't get easier. And so the general strategy is to stick to flux-based variables as soon as a Josephson junction is involved. And that's what I suggest we do. Good. One more complication that we don't deal with in normal conducting circuits much. Suppose that you have a superconducting loop here interrupted by 2 junctions, and there's a magnetic flux threaded through that loop. And maybe that magnetic flux might actually change as a function of time, in which case there's an EMF voltage induced in the circuit loop. And that will modify Kirchhoff's voltage law, right? This EMF voltage will have to be included. And once we integrate this relation, which is indeed for voltages, if we integrate that once, we get a relation among the generalized flux variables, and this integration constant here on the right-hand side, it turns out that superconductors only allow that constant to be an integer multiple of the flux quantum. I haven't derived that here. It's a slight diversion that we don't have to worry about right now. And so these constraints from Kirchhoff's voltage law, they now have to include external flux. And there's certainly a question as to how is that actually done systematically in circuit quantization. And before I continue, I'm just going to stare over at Michael. Michael, are you just worried that this will break down again, and that's why you're here? Okay, that's fine.
This time I don't have to run.
Okay, Thank you. You're welcome to stay, of course. So let's talk a little bit about how in the circuit quantization procedure, as described, for instance, by Michel de Vore in his articles, how do we do that systematically? How do we handle these loop constraints? And here's an example of a circuit that has been studied and is being studied in Dave Schuster's group. It's an interesting circuit, but I won't talk much about its functionality and properties. But we'll use it as an example of something that has more than one loop. And in this circuit, there are 3 independent inductive loops. So I've already denoted the 3 fluxes of relevance over here, and we could ask, well, how do we take care of the arising constraints? And this is typically done with a spanning tree and closure branches, and so those are simple concepts that I will briefly talk about and explain. First of all, the circuit has 5 nodes. Nodes are the places where branches meet. So whether I draw the node in this position or this position doesn't matter. And essentially, this entire connecting region is one of those 5 nodes. And I have the freedom to declare one of those nodes to be ground. So I picked the one on the bottom here. And once that ground node is chosen, the concept of spanning tree is simple. A spanning tree is a set of branches that connects this ground node to every other node in the circuit. So I've picked my ground node, you pick some other node, and if I have a complete spanning tree, then there's a path from the ground node to that other node, and in a given spanning tree, there's only one such path. Overall, spanning trees are not unique. You see that despite the fact that the circuit is symmetric with respect to reflection along the vertical here in the middle, I happen to pick different paths on the left as compared to what I did on the right, and that is perfectly fine. You'll get different expressions in your Lagrangian, which are all equivalent by shifting variables, so no worries there. The branches that are outside the spanning tree, those are called closure branches, and each closure branch closes one particular circuit loop. Now, the capacitive loops here we can basically disregard. It's the inductive loops that count for flux in our case here, and so those are marked in whatever color I picked here. I did this overnight. I never asked what this color was. It might be orange. Okay, I'm colorblind. This is haunting me. And again, yeah, the capacitive closure branches are irrelevant for us. Good. And then to obtain our Lagrangian and incorporate these constraints from Kirchhoff's laws, what we do is we can write down a Lagrangian that ignores these fluxes first entirely, and then once we look at our something weird happening again on my computer. I saw that there's some question. Yeah, something strange is going on. Okay, but we'll continue and hope for the best. So Lagrangian obtained, kinetic minus potential energy, you know the story. And then to incorporate the constraints, what you can do is you pick each closure branch has a particular flux variable. I'll call each of them phi sub j. And then for this branch variable gets replaced, right? Remember that in Kirchhoff's law, you go around the loop. This branch variable happens to be one of the branches forming the loop, and so if I add up my fluxes around this loop and include the external flux, I have to get 0. And so we incorporate this constraint by saying, well, we have our spanning tree, and it's the closure branch variable that we substitute and replace by the expression that is the remainder of that sum. So the other flux variables in that loop, as well as the external flux. And that is how you can incorporate all those constraints. Good. And then, we could now continue for this circuit. You would go through the rest of the steps. You would have to derive your canonical momenta, perform the Legendre transform, get your classical Hamiltonian function, quantize that, and then get through quantization to a matrix representation of your Hamiltonian. I'm not going to run you through those steps because they are tedious, but they're systematic, and we'll see in a couple of moments that indeed they're systematic enough so that we can explain to a computer how to do that for us. Meanwhile, Chen, were there more questions that I should address at this point?
There are questions about how to add external flux or charge drive. I think probably you will address later, right? Or
perhaps I won't.
Yeah, maybe you can briefly comment on that.
And the question is about the charge drive, you say?
About if there are AC external flux, then what term would be added to Lagrangian Hamiltonian? Or let's say AC external charge drive, then what would you do to the Lagrangian?
Okay, yeah, those are very different things. So let's stick to the flux case first. If there's an externally driven time-dependent flux, then there's actually a paper for that we published an early paper, and then there was follow-up work by David DiVincenzo's group showing that one has to be a little bit more careful when the flux becomes time-dependent. So the spanning tree story is not complete if you apply it naively in that case. So that's an advanced case that I do have slides for that, but it would take quite some time that maybe I don't have right now. But if there's time at the end, I'll be happy to discuss that. On the charge-driven case, so you would have a voltage drive attached to the circuit through a coupling capacitor, I imagine. And if you do that, then you would just treat the voltage that your generator provides as a C number field, and so you would have a variable for that coupling capacitor, a flux variable that basically is composed of that given classical voltage minus the voltage on the other side of the coupling capacitor. So that branch variable becomes sort of the difference between the C number imposed by the generator and the node flux on the other side of the coupling capacitor. That's relatively straightforward.
Okay, then there are people wondering whether there exist textbook or problem sets containing exercises to solve superconducting circuits relevant to quantum computing.
Yeah, so there's even in the original article, which was a Lesouche lecture actually that Michel gave quite some time ago. There is an exercise in that already. I think that exercise is again present also in the updated version, which is the paper by Devoret and Vool, VOOL, and then there's another paper where the first author is currently escaping me, but there's a newer sort of circuit quantization tutorial, and I'll be happy to I imagine that you have a way to send material to participants, and I can make a list of references and share that if you forward it.
Okay, yeah, thank you.
Okay, good. Now, here's sort of the overview of some of the things that we're leaving out, but that have to be implemented if we want a chance for a computer to do the job for us. So I'll briefly go through this because it gives you a flavor of some of the things that are involved and maybe not completely trivial. So we start from the circuit diagram. You're now familiar with this analysis. I briefly in passing mentioned what I mean by nodes and branches, and you would enumerate them. You would denote what all the loop fluxes are. You would construct a spanning tree and identify closure branches, and then from there move on to formulate a Lagrangian and eliminate constraints. And then there's a topic that I haven't addressed because the example that we looked at was too simple. But if you have a larger circuit, then of course you're welcome to start with the kinds of variables that we looked at in the example, which were branch variables. They were fluxes across our circuit elements. But depending on what your circuit looks like, those variables may actually not be the most convenient ones, in that some degrees of freedom might have certain properties that need to be respected on the quantum side. For instance, if you think about your simple harmonic oscillator, there's no choices to make, but its potential is such that it's confining, right? If you imagine placing a particle in a harmonic oscillator potential, then that's a confining potential, and the wave function of that particle has to approach zero sufficiently quickly as you go far away from the origin. That's what I mean by extended or confining. In the case of a transmon, remember that the potential energy there is not a quadratic potential, it's actually a cosine. So that's a periodic function. And on the quantum side, we'll actually have to include that in our boundary conditions for wave functions. So it becomes very important that your choice of variables is aligned with the nature of these degrees of freedom. And it's important that we identify which degrees of freedom are periodic, which ones aren't. And then sometimes there's an opportunity to simplify a circuit, perhaps because you have conserved quantities. That's what I mean by free or cyclic. So choosing variables in a smart way, some of that we know how to teach a computer. Some of it is actually quite not very well understood and known. Even if we identify what's periodic and what isn't, there's still, depending on the circuit, there can still be freedom left that where it's much harder to say, well, what variables should we use in that remaining subspace, if you will. And so there's still research also in going on in that direction. Now, once we have the Lagrangian, everything is peachy, and we make it to the Hamiltonian no problem by going through the Legendre transform. Formally, that will involve inverting the capacitance matrix, which is, by the way, one of the sort of indicators that the idea that you can just guess a Hamiltonian for a complicated circuit is suspicious to me. So unless you somehow have means for inverting larger matrices in your head, I don't know how to do that. So probably don't get tempted to skip steps and just guess the Hamiltonian. That can go wrong. Once you have that, though, canonically quantizing it is what leads us to our Hamiltonian matrix. Once you have chosen an appropriate basis, which could be the charge basis, as we'd like to use it for a transmon, it could be harmonic oscillator basis. If we don't know anything smarter, then we might also discretize in position basis. I'll talk a little bit about hierarchical diagonalization, perhaps. Chen, can you give me a little bit guidance here on when would you like me to just shut up and be done?
Yeah, so the lecture has allocated a total of 2 hours. Even though some speakers may just decide to do 90 minutes, including questions. So I think you can decide on your time, and
Wonderful.
Of course, you probably will not speak all the way for 2 hours. So we definitely will have some question time in the end.
Sounds good. Okay,
but
great.
otherwise we have plenty of time. Yeah.
Great. Okay, then I'm less worried about the lost time. So you see on the circuit quantization side already, there are plenty of indicators that there are things that we have to do over and over again. And this is something that we noticed in my group over the years. And here are some of the tasks that if you're interested in superconducting qubits, you work with them in the lab, that you'll have to go through repeatedly. Like, you will want to know what is your qubit's energy. You will want to compute energy spectra. Maybe to get intuition for certain things, you will want to understand what the wave functions of your qubit look like. If you want to couple your qubit to some other circuit, like a resonator or something that allows you to manipulate and read out your qubit, you'll want to know how strongly does it couple, and that involves calculating matrix elements. If you care about your qubit, then you care about its coherence time. So probably it would be nice to also have ways to estimate coherence times. We have some simple ways to do that through, in most cases, just perturbation theory based considerations. And then, as I said, one qubit on its own is no good. So you probably want to couple it to more qubits, to oscillators and such, and have a streamlined way to do that. And then hopefully simulate your system. Perhaps before you switch to time-dependent evolution, doing parameter sweeps over such a coupled system can sometimes shed light on where you want to operate and where you don't want to operate. And then once you've determined your operating point, maybe you want to figure out how to do gates, right? And simulate your gates, figure out how high a fidelity you expect given the loss and dephasing mechanisms that you're aware of. And this is where SE Qubit says, well, for time evolution, there's actually a fantastic package that we love, and that there's no need to duplicate any of that. So all that SE Qubits does is try to do a good job providing an interface that will then allow you to perform simulations on the QTIP side. And so for instance, you can get your Hamiltonian in Q object form, which QTIP likes, and we're still working on adding more functionality that will kind of make it easier to identify and construct jump operators, drive operators, and all these things. Okay.
Good question, yes.
Yeah.
Can all the first part of the talk be achieved optimally by SD qubits?
Optimally. That's a loaded word. What can I ask back what optimally means in that context?
We'll see.
Maybe the back and forth is difficult in the webinar format. But
yeah, so how about you just let's just take off the word optimally. So is what you taught in the first part of the talk basically taken care of by SD qubit, that you can just run that automatically?
Yeah, I would say yes. That's at least our goal. And if people discover that we fall short somewhere, then we are actually grateful to get feedback and hear from people and improve things. But yeah, our goal certainly is to cover all these things. That's part of the message indeed. Okay.
And also another question, wouldn't inverting a capacitance matrix cause non-nearest neighbor coupling Hamiltonian?
Oh yeah, sure. Absolutely.
And does it sound weird, or
that's what circuits do. Weird or not, but that's what circuits do.
Okay.
Okay, I'll skip over the storing and sharing data, and I may have we'll look at examples of exploring things interactively, which is both fun, but also a place where I think it's helpful to sort of get intuition in the beginning. Okay, and indeed, so the message is that this Python package, which we released at the very end of 2019 in sort of version, I don't know what we called it, maybe we called it version 1 or maybe we called it version 0, I forget. But that package is there to accomplish those tasks. It has its place in research. So my group and I use it for research for sure. I've also heard from some people who use SE qubits in the classroom in some simple settings. And then this last point is sort of more an anecdote where you know I think in physics we don't always get great training in scientific coding. We sort of just do whatever works, and when it works, we don't worry about much else anymore. Sometimes that is kind of sad. Like when you ask, maybe ask yourself whether you're still doing debugging by using print statements, and if the answer is yes or yes most of the time, then there are better ways. So for us, this has also been a nice place to just improve our coding skills. Good. A couple of numbers here. The package can be easily downloaded through the Conda package manager as well as on PyPy. So you can also use pip to install it. The number is the download number, current one on Conda is around 136,000. So we're happy that people are actually downloading this. Don't mistake this number for the number of users. That's not how this works, but that's the only reliable number that I have easily access to. And there are now by now 2 papers on sort of some of the aspects of this package if you're interested in understanding how some works sort of under the hood. Good. And then last but not least, before I try and jump into a Jupyter notebook and show you some of this in action, I should note that there are certainly situations where lumped element description of a circuit can fail. SE qubits is based on lumped element description. So if you need something fancier, then that would be beyond SE qubits. On the other hand, otherwise, it tries to not make additional assumptions or approximations. So for instance, when we'll look at a transmon qubit in a moment, there's no approximation or expansion of the cosine potential, for instance. It really does what the circuit demands. And in many cases, that's helpful because we might actually want to understand how high the charge dispersion is in levels 2 and 3 in some circumstances. All right. Now, since my computer completely crashed in between, I will briefly pause here my screen share so that I can get my Jupyter notebook up running. Meanwhile, if there are questions, please let me know, Chen, but I'm going to have to fire up my Jupyter.
Let me ask a few somewhat general question. One is that what would you recommend for physics grad students to practice to improve coding skills?
Oh, that's a good question. So work with somebody who is willing to look over your code occasionally and have discussions about coding. Like in physics, oftentimes really our attitude is, you write code, you don't comment it. Once the paper is written and finished, you don't care about the code anymore, and it sort of goes dormant. And God have mercy on the person who needs to read somebody else's code in that situation. It's very painful. So there are also some good books on coding. I think that there are simple things that not everybody's aware of that you can find everywhere. Like for instance, in Python, it's usually good to avoid for loops because they don't get parallelized. Not everybody knows that, but there are good books, also great online resources that sort of talk about what is Pythonic coding, and similar things, of course, exist for other languages as well. Okay, I'm ready.
Okay,
I think.
yeah. So are there any sandbox repositories using Qtip that you guys know of where we can look at examples?
Examples for good coding in Python.
No, for Qtip. For like
physical examples in Qtip.
But Qtip has fantastic documentation with lots of tutorials, as far as I recall. So I think they have plenty of examples with code online. Okay, I'm going to go back to sharing my screen here.
Yep.
Let's share. All right. So now let's hope that this works. I have lots of Zoom stuff floating around. There we go. Okay, so I'm going to show you a little bit of the downside of doing live demonstrations while Zooming is that Zoom, at least on my computer, consumes a lot of resources. So everything that you see on my screen is going to be radically slower than what you would see if Zoom wasn't running, but we'll try this nonetheless. So all I've done is I've imported SEQbits with SEQ as the abbreviation. And then what you can tell is that if you've ever played with SEQbits, then my graphical user interface looks slightly different. That has to do with the fact that I've been refactoring the old one. This is going to be released anytime soon. But all the functionality.
Also, people are wondering, would the Jupyter notebook be shared? So I imagine you have some standard examples there people can play with, right?
Yeah.
Maybe you can comment on that.
Yeah, so if we end up doing something very special that is not contained in the existing demo notebooks, of course, I'll be happy to share that. But we have this repository that is full of examples. So maybe real quick, we can just Google for SEQbits. We can head over to the online documentation. And if you want examples, Jupyter examples are up here, so you should get a link to the GitHub repository from which you can just clone all the Jupyter notebook examples. Yeah.
Thanks.
All right. Now back to here. All right. So this is our one of the graphical user interfaces. This is the one that shows one qubit at a time. And it gives you a flavor of the qubits that are currently hard-coded and well, optimized or not, but we try to make them fast. If somebody has better ideas of more speed up, I'm all ears. So you can pick among qubits. Let's maybe switch to tunable transmon. If you're not sure what that means, then under qubit info, you can actually get an infographics that says, this is not the tunable. There we go. It's just delayed. There we go. This is the flux tunable transmon with a squid loop external flux that allows you to tune the frequency of your qubit, which is already displayed in the view graph down there. And so if we head over back to main, you see that you get to play with these sliders that are the various parameters that enter the circuit. So for instance, we could play here with the charging energy. I could make it a little bit larger, and then it'll recalculate and display the new graph. Everything sort of in slow fashion right now on my computer. So let's maybe go back to Transmon here and talk about some of the simple things in more detail. So you can pick what scan you want to see. Right now it's showing the lowest couple energy levels as a function of the offset charge. Transmons are fantastically insensitive to offset charge in its lowest couple levels, so you don't see much movement. If we go to literature parameters and actually switch to the Cooper pair box regime. So this is Michel's original 1998 paper. You can tell that there's a lot of offset charge dependence. And if I switch off the subtraction of the ground state energy, we can actually see the charging parabolas. There we go, right? So this is energy spectra as a function of a parameter that you might want to scan over. You can look at the wave functions. They will look funny for the Cooper pair box represented in this way. So we can maybe switch back to Hanhi's parameters. There we go. That looks a lot more transmon-like. You can barely see that it actually is not a parabola, but bends back into a cosine. You can look at matrix elements. So going here, this is now the charge operator matrix elements plotted in absolute value. If you're colorblind like myself and don't like 3D, I think you can actually display values on top. There we go. I find that super helpful. This was something that Peter Goszkowski, I think, originally discovered and programmed, which is very nice. And then if you want to see matrix elements as a function of some parameter, there's a matrix element sweep. This one looks somewhat boring. For Fluxonium, matrix elements tend to be quite crazy. Let's take a look. And it's thinking. Oh, it's still thinking. There we go. Yeah, matrix elements for Fluxonium are crazy, indeed. And then last but not least, there's another tab where you can look at estimates of coherence times, and those are even slower to compute. Probably, I don't know, maybe I'll give up on it in a moment. On your computer without Zoom running, it should be relatively fast. So this is a simple graphical user interface that allows you to explore individual qubits. You saw me sort of do this in front of you. It didn't require any coding except for 2 lines entered in the Jupyter notebook. So this is really meant for beginners. There's something was flashing. There's, of course, SE qubits is not this graphical user interface. So we'll jump a little bit later into a notebook where there's actual code, and we'll again explore this a little bit more. But this is sort of one entry place where if you just want to learn about superconducting qubits, what they are, how they behave, then this can be a nice starting point. Okay. Any more questions at this point?
So does SE qubit allow us to make our own qubit classes? Yes.
Let me see in what order I want to go through this. We can do that now. I just have to then we'll just jump over there for now. So when you say make your own qubit classes, there are 2 ways in which you can think about this. Number one, of course, you're welcome to fork SE qubits and modify its code. And ultimately, when things are running, if you have sort of a hard-coded new qubit that you've optimized, then making that class available ultimately would be great. So that would be just writing a new class that inherits from certain parent classes that Transmon inherits from qubit base class, for instance. And so there's a lot of functionality that you will not have to rewrite. It's essentially the specific Hamiltonian and how you want to diagonalize it that would have to be put in place if you have a brand new qubit. However, the simpler version, where you don't have to kind of go into the SE qubits code, but rather use existing code, is this submodule of the package that allows you to enter a new circuit in graph format, essentially. And that was something that I wanted to talk about for a little bit, and we can do that at this point. So the circuit that is here on the screen is, again, the 0-pi circuit. That happens to be one that is actually hard-coded as well, but I'm just using it here as a relatively simple example for something that you can also enter yourself, just like any other circuit, and then try and get spectra through this custom circuit module. So how does that go? That module basically runs through this forest of steps that we discussed already before. a number of things that need to be put in place so that you make it from the circuit to a Hamiltonian. And along the way, it does a good job of distinguishing these different types of variables, in particular extended periodic and free ones. And then, as I mentioned, there may still be freedom left where SE-qubits is not particularly smart, and maybe we can help it or sort of in the future to get smarter. We'll find out. So for the 0-pi qubit, how would you enter that circuit? The format in which this is entered in code language is relatively straightforward once you get used to it. There's actually and I'll send information about that around as well. There's a wonderful little package that a student at Yale recently shared with us that allows you to drag and drop elements onto a canvas. And once those are connected, it actually produces this little code block with a description. So that exists, but I'll just talk about the description for a moment. So the 0-pi circuit is a circuit with 4 nodes. I've enumerated them 1, 2, 3, and 4. And you see that those are the numbers that enter here in columns 2 and 3. The first column just says, what element am I talking about? That's relatively self-explanatory. There's Josephson junction, inductance, and capacitance. Then again, those 2 numbers say which 2 nodes are being connected. So apparently there's a Josephson junction connecting nodes 1 and 2. Here's node 1, here's node 2, here's the Josephson junction. And then the rest that follows is sort of a combination of either just numbers, in some cases maybe a symbol as well. For a Josephson junction, the 2 entries are EJ and EC, because our Josephson junctions carry its own junction capacitance along. And so we give values for both of them. For the inductor, it's EL, the inductive energy. Capacitor is the charging energy. All by default expressed in units of gigahertz. That's out of the box. SE-qubits works in those units, but there's you can change that option if you really want to. And so you enter your circuit in this kind of format, and then everything is relatively quick. So you would take this was entered as a string, as you saw on the previous slide, and then it gets entered, or it becomes the first argument of the circuit class. And then the from file equals false. It goes back to a time when we imagined that people might read this from a file, which I think should maybe not have been the default. But so right now you have to write from file is false. It's just a string here that gives the description. And so then the circuit module, and here the circuit class in particular in that module, is going to do an analysis of this graph for you, going through all the steps that we discussed. And so the next thing that you could ask is, well, what do you think is the symbolic Lagrangian for that circuit? And here we're asking for that to be expressed in terms of node variables. Internally, SE-qubits works with SymPy. I would argue that a human would rewrite this expression probably in slightly different form. But that's simple to do, and probably most of the time I don't care that much about the symbolic Lagrangian. But this is the correct symbolic Lagrangian for 0-pi. That much I know. And you see that it does insert the external flux here, so that's taken care of already. Internally, it actually decides that it doesn't want to use the node variables. They're not the most convenient ones because they're not aligned with periodic and extended and so on. So it makes a choice, and you see that the new variables actually only go from 1 through 3, I think. So theta 1, 2, and 3 are new variables. Meaning that a fourth one already has been eliminated. That's great. And you can inspect what that variable transformation actually is. You might be interested, right? You know what the node variables are, but what are the new variables? You can output that transformation. You can even overwrite this with your own transformation when needed. And then you can ask it, well, what are the kinds of variables that you've identified? And it's identified 1 periodic and 2 extended degrees of freedom. And that is listed here. Okay. Then we get a symbolic Hamiltonian. That's fine as well. At this stage, you see that offset charges are being included as well. So there's not just external flux through that loop, but also offset charges that might affect your superconducting island in the circuit. And you know, all of that allows you to simply use things like the eigenvalue method to get eigenenergies. One thing that I didn't put on a slide, but it's actually important, and maybe I'll somehow share that as well when I forward material to you, Chen. There's definitely a need for whoever works in this format with SE qubits to be aware that there are cutoffs, matrix size cutoffs, that the user needs to check whether convergence has been reached. Let me try and illustrate that in a very simple setting. So if you think about a transmon qubit, chances are that when you've written down your Hamiltonian and you ask yourself, well, what kind of matrix do I write down? You'll recognize that the matrix that represents the Hamiltonian of a transmon qubit is infinite dimensional. It doesn't have finite size, and our computers don't like infinite matrices, so we have to truncate. And our current philosophy is that truncation, there's in some places there are heuristics that would allow us maybe to provide guidance, but at the end we're placing the responsibility with the user to check that truncation levels have been chosen appropriately so that the energy levels have converged, and so that's something that you should always do. Don't forget that. More questions, Chen?
So there are a couple questions regarding the simulation result of T1, T2 times or qubit performance in general. So
yeah.
Do you calculate T1, T2 from some sort of input noise spectra, or is it from previous data from publications? And how do you take into account of the impact of material quality?
Yeah, so those are very good questions. Let me try and answer them by going into our documentation, and that will shed light on some of this. So if you go to user guide and you jump into coherence times, then let's say you're interested in depolarization. So what you find is a discussion of the various channels that you can include and that are supported. So there's T1 due to capacitive noise, inductive noise, flux bias line noise, quasi-particle tunneling. And in each of those cases, you see that we provide expressions and hopefully in some place joined by there we go, by references from which these expressions were extracted, so that you know what is actually being calculated internally. Of course, if you don't do anything special, SE qubits will assume certain default values for things like, well, let's suppose we're talking about dephasing due to 1/f flux noise. It'll make some assumption about a typical noise strength for your 1/f spectrum, the noise amplitude, right? But all of these things can be changed. So for instance, if we were to hop over to dephasing 1/f noise, so you actually see what the default value is. Here's the low frequency cutoff. due to the nastiness of 1/f spectra, there's even an experiment time that enters somewhere. Here's the noise power. Here's the amplitude of the noise. So all of these things are you can change as options of the function calls or method calls that indeed compute these contributions to T1 and T phi.
Yeah, thanks.
Okay. Maybe one other thing to just make sure we're all on the same page about this. I try to emphasize that I consider this estimates of coherence times. I would claim that in most examples of papers where we and other people compare coherence times experimentally to theory, there's a fudge factor or fit factor coefficient somewhere that sort of aligns the two to some degree. So the idea that we could just compute and predict coherence times from scratch with high accuracy, that's, I think, unfortunately, a world that I haven't discovered yet. And of course, that situation gets exacerbated by painful things like, if you measure your T1 for long enough, Jen, probably you'll report that it's not constant as hours pass by. It might switch over time to some other value, and maybe you have a bad T1 for 15 minutes, and then maybe it switches back if you're lucky. Maybe it doesn't. Those are things that are completely outside of the realm of stuff that we can predict currently.
Yeah, absolutely. So just to be clear, there are lots of assumptions going into this package that you can change. Those are dependent on the raw materials and dependent on the environment of the experiment.
Yeah, and also a good thing to point out, there are places probably in T1 there must be a place where temperature might enter, right? If you're not at zero temperature, so you might want to investigate whether there are excitation processes that can bother you. And it's good to read the documentation, because if you don't read that this temperature is to be entered in Kelvin and you enter it in something else, you will get something else, and probably that something else will not be very meaningful. Yep. Okay. Now, I still had a couple more slides that I skipped over, I think. Right. So on the circuit module thing, we were nearly through a rough overview. There was something I wanted to briefly mention for people who are really interested in playing with that part of the package. So there's no real magic here in that the simple fact that Hilbert space gets big very quickly as you increase the number of nodes in your circuit, that problem is still very much there. And depending on how you approach that, it might just prevent you from doing anything meaningful. One thing that might help is a naive kind of hierarchical diagonalization, which I'll briefly illustrate here. So this is a simple circuit here. What I see apparently is that there's a transmon here, a resonator, which I'll just take into account a single mode of this and treat it like a single harmonic oscillator. There's a second transmon, a second resonator, and a third transmon. And so if you imagine for a moment that to get the energy levels of the transmon, maybe you're very generous and you make it 100 by 100 Hamiltonian in charge basis. And then maybe the oscillator is trivial because you know how to diagonalize it by hand already. And so you just keep into account, you'll just take into account the five lowest states. But then you have 3 of these 100 by 100 matrices, 2 of the 5 by 5. And if you multiply that out, then you'll get a 25 million by 25 million matrix. And of course, we could now argue about how sparse it is, and maybe it's still doable. But I think the message is very quickly, make it a little bit more complicated very quickly. Eventually, it will not be doable unless you do something at least marginally smarter. And so here's the one way in which SE-qubits tries to help you do something marginally smarter. So when I say hierarchical diagonalization, all I mean is we'll treat this problem in multiple stages. So in this particular example, I would say, okay, probably you're interested in parameter regimes where the coupling between these individual subsystems is not super strong. So it's not like everything just wildly hybridizes, but probably you're somewhere close to the dispersive regime, if not really inside the dispersive regime. And so in that case, it would be valuable to first find the eigenenergies and eigenstates of the individual subsystems. And once we have those, we can truncate in their bare eigenbasis, right? So for the transmon, I might decide that, well, in the eigenenergy basis, I only need the lowest 5, maybe. And if I do that, then I end up with a situation that looks like this. Of course, I now have to compute a new matrix that takes into account these transmon eigenstates. But that matrix is now just slightly above 3000 by 3000, and that's feasible, right? And so there are ways in SE-qubits which are documented as well. And I think in our example notebook we have some code, explicit code examples as well, where you can specify this kind of hierarchy, which basically consists of identifying subsystems that you think are going to be helpful to consider as weakly interacting. And then it will go through this multi-step process of not doing the diagonalization in one go, but doing this in multiple stages, which keeps the overall matrix sizes in check and may actually allow you to accomplish something that otherwise wouldn't be possible. Okay. Now, I can talk for a little bit more about sort of an intermediate stage, which might be helpful to people where, suppose that you have 2 transmons coupled to a resonator. Do I really have to do this with a custom circuit module? Isn't there some simpler scheme where I just put multiple subsystems that already exist into a joint Hilbert space and work with that way? And the answer is yes, that we can do that, and that's relatively simple. I could talk about that. I could also if people have to go and we feel like we're all satisfied, I don't have to do that. So Chen, you're the boss.
We already have question about it, and I think that's really important. People want to know how to put a qubit and the resonator together, or 2 + 1. That's a very very widely used user case. So it will be good to talk about. Yeah.
Sounds good. So I'll jump into the shortish version of that. There's also an example notebook, which I had actually executed first so that it wouldn't have slowed me down. But since my computer crashed in between, that's lost. So I'll do it with slides. But there is an example notebook also for this. So here, 2 transmons and a resonator. And how do we do that? So in SE-qubits, various ways to create an instance of your qubit. You can do that purely programmatically with code. There's sort of an in-between way, which is not the full-blown graphical user interface that you saw earlier, but you can kind of get a little bit of help if you say tunable transmon.create. It'll produce a qubit instance of this type, and it will start with default parameters of some kind. And it'll display this on your screen for you so that you know what the parameters are. You can edit them, and it'll update them on the fly, right? So that's if you're working inside a Jupyter notebook, this can be a nice way to just define your qubit and not wonder whether you've forgotten some parameter. And so I can do that with 2 transmons and a resonator as well. And so now I just have these three objects, but they don't know about each other yet. And I can tell them about each other by defining a Hilbert space object. That one also has a little user interface where what you do is you can select the individual subsystems that you want to participate and belong to that Hilbert space, and then you get to define interaction terms between them. And so you see one example here where I've created one interaction term, and then I've chosen to, perhaps I'm lucky, my interaction term is just of that kind, G times operator 1 times operator 2. And so I pick which 2 subsystems are involved, transmon 1 and resonator. The transmon couples through its charge operator to the resonator. The resonator should have an A plus A dagger there. This one is just the annihilation operator, but note that down here it says that we're adding the Hermitian conjugate, so that'll take care of that. And then I entered the interaction strength, and ultimately this just clicking on create Hilbert space object, and that will create that object for you. Again, no need, if you don't like graphical user interfaces and you prefer just the coding way, that's fine. All of that is can be done without any interference from graphical elements as well. And then there's what you get back. This Hilbert space object immediately allows you to get eigenenergies and eigenstates of the interacting system. That's important. You can also run parameter sweeps on this composite system. I wonder whether, yeah, here's one simple example of perhaps something useful. So for this system of 2 transmons coupled to a resonator, what I specified for this parameter sweep was, yeah, I'm lying here a little bit. This plot actually belongs to flux tunable transmons. I apologize, I should update this. So my 2 transmons are actually flux tunable. They have slightly different squid loop areas, which is why their flux period is slightly different. And with this parameter sweep, you can then sweep over external flux and produce plots that actually are somewhat reminiscent of two-tone spectroscopy. And we've put some functionality in place, which maybe it's nicer to show you in the documentation, where it's a little bit more comprehensive. You can specify which transitions you want highlighted. So if we do parameter sweeps, composite systems over here, then here's an example. It's a lengthy example because there's lots of stuff that goes into it. And then here you see a plot, in fact, the same plot most likely, where you can pick how to do coloring, right? Usually, if you don't do anything special, you get kind of spaghetti plots like this, where it'll be on you to kind of figure out as the detective, like which transition is which. But with this parameter sweep, you can actually specify that, well, please highlight for me just the transitions where I'm dispersive and I'm making a transition that excites transmon 1, but nothing else, right? And that's what's highlighted here. You can decide to include multiple subsystems as highlighted. You can pick the initial state from which you think the system should start. Like if you're thermally excited, maybe you don't start in the ground state and you see other transitions, you can do that. You can include sidebands, all kinds of things which hopefully make the analysis of these plots. And I'll look at this. Jen, are you still there?
Yeah. Yes, you were breaking you were like
Okay.
breaking up a little bit, so we were a little bit concerned.
Okay. This
It's all right.
is interesting. So okay, this is interesting.
Yeah, not breaking up too.
It's
all right.
interesting.
Yeah, not breaking up.
So
Breaking up too.
It's all right.
interesting.
So Jens is back in time, Chin, so we're slowly catching up to the present. Jens is back in time, Chin, so we're slowly. Jens is back in time, Chin, so we're slowly. Okay, now we're in the present.
Now we're in the present moment, but not on my computer anymore. But I think so. I had covered all the slides that I wanted to show. Maybe this is a good point to answer more questions if there are any.
Sure. So let me see. So Jens, there is a question asking.
Oh, now I can't hear you. Wait.
Yeah,
And
can
Michael
you
ran
hear
away.
me?
I have to figure out Michael's computer. Can you say something, Jen?
Hi. Can you hear me?
Michael. Michael? I can't hear anything on your computer. There's no audio on your computer.
Exciting.
This is very exciting. Oh, and
Okay.
people are sending
Well,
laughing faces.
That's not. Well, assume they're doing so kindly.
I get a lot of crying faces.
All right. Excellent.
Okay, can you hear me now?
Yes, I can.
Okay, so there's a we have an audience asking whether you know of another package called SQ circuits from
Yes,
ladies
yes,
group.
and I apologize. I apologize that I didn't mention this yet. So there's that package. There's also a package from the Netherlands, which is more based on expanding the cosine. So there's an additional assumption that things are close to harmonic. The package from the Stanford group is very nice, and I think it's been an interesting race where I think there are places where their package currently is faster and better. There are hopefully places where the opposite statement holds. But yes, the custom circuit functionality is not unique to SC qubits. That's correct.
So what are the differences? I guess that was mainly the question was about. Can you compare like differences in functionality between your SC qubit versus the few others out there?
They're in some places quite similar. I think the last I heard where the Stanford package is ahead is that they include automatic differentiation as part of their functionality. So they use I don't know whether it's AutoGrad or whichever package. Like if you're in the business of trying to optimize circuit parameters, it can be nice to have that directly built in. That's something that is not implemented in SC qubits currently. So there's some differences, a lot of things that are similar.
Okay. So do you have more slides to tell us about, or should I just
no slides? There's something very strange going on with my poor little computer. but I'm serious that this there was a summary slide which we're missing now, but I can give the summary in words. You remember the overview of the lecture that I gave, maybe as slide 2, which said, we face this issue that experimentalists are great at building circuits, and we're interested in understanding them and maybe making good use of the fact that the transmon may not be optimal for everything under the sun. And so working with different kinds of qubits, exploring them requires circuit analysis, circuit quantization, and then in most cases some numerics. And so I hope that I conveyed how to do a little bit of that by hand, and then showed that there are tools now that don't require you to do that in every instance. Like some things are in SC qubits as well as in other packages.
So there's a question, maybe I'm missing the context. Doesn't SC qubit also use harmonic oscillators as basis states?
Oh, there's a very big difference between the choice of basis and whether or not you expand the cosine. So for the transmon to begin with, we do not use harmonic oscillator states. We work in charge basis. For fluxonium, we currently internally use harmonic oscillator basis, but that doesn't mean that we're expanding anything. It just means that you need to make a choice for what your basis states are so that you can represent your Hamiltonian operator as a matrix. For fluxonium, that may be harmonic oscillator. You could also discretize. You have to do something, but that's again very different conceptually from the question of whether you overall make an assumption that your system is only weakly anharmonic, and we don't make that assumption.
So there's a question of interfacing between the Hamiltonian you produce and the Q-tip simulations. So can we somehow like import the Hamiltonian generated into Q-tip?
Absolutely. So if you work with a Hilbert space object, then what you get back when you call the method Hamiltonian, you actually get a Q-tip Q object back, which you can directly stick into MESOLVE or SESOLVE. We're also, I think we have in the last release, and maybe there's a little bit more coming in the next release, added kind of helper functions that should make it simpler to also generate the kinds of operators that want to go into like the position of MESOLVE where you have to specify the jump operators. Right, those are separate from the Hamiltonian, and you want to make sure that these things are properly, identity wrapped. Right, if you say your jump operator in a composite system consisting of a transmon and oscillator, your jump operator is A, then you need to make sure that depending on how in your tensor product structure, maybe the transmon is first, so you'll need identity tensor product with the annihilation operator. And so there's also sort of helper functions that accomplish that and make that easy.
Yeah, a couple more questions. How do you decide the cutoff for states, like with harmonic oscillator basis or discretize the charge or phase basis? So how do you decide on the cutoff Hilbert space dimension?
Yeah, I mean, for the most common circuits that we work with, I think there's sort of some ballpark typical cutoff values that are okay in typical parameter regimes, and we probably those are the ones that we picked as defaults in some places. But really, what you should do is calculate your energy spectrum once for your first guess of what this cutoff might be. Maybe you use the default, and then recalculate it with an increased cutoff and make sure that all the eigenenergies that you're interested in differ by less than whatever you consider your accuracy threshold.
Well, then there's a specific question about off-resonant drives on transmon can influence the spectrum and create like chaos, a la Blaise paper. So are you planning to take into account in your library and in terms of off-resonant drives and chaotic regime? Yeah.
So if this is a question about are we going to simulate dynamics within SE qubits, then probably I would say no for now. But if there are situations where all that your drive does is give rise to an effective constant shift, that may be doable. But as soon as dynamics really is involved, then we're kind of on the side of Q-tip will be involved, and it's I don't see any benefit in competing even with Q-tip, right? If there are certain types of dynamics simulations that become standard and common for certain systems that tie into Qtip, then probably that would be an extension to Qtip.
Okay, so finally, can we use these approaches for doing research numerically and report it as an article? I guess my interpretation of this question is the use of SC-qubit as a package in their research and publication.
Yeah, absolutely. I mean, it's nice for us to receive citations. It helps us to apply for continued funding and make sure that the package doesn't die a horrible death. But you know, even if you don't cite us, it's not a crime. So the answer is yes, of course. It's a tool that is not meant to you know, just sit somewhere and not be used. If you find it useful, by all means. That's great.
All right. So I think there are a couple questions that are a little too open, I feel. Maybe specific to this class, to this lecture, and if people have more questions, I can take a look at another one or two. If not, we'll thank Jens for giving us a fantastic class. And
well, my apologies once more for the huge technical difficulties, and thanks to everyone for being patient with that. I apologize.
Okay, yeah, thank you everyone for joining us today. And just a reminder, on Friday, we will go a little bit more experimental. So Wei Dai is going to tell you now about how about actually drawing up the shape of your capacitors and the Josephson junctions in a numerical package, and how to actually design a blueprint that you can fabricate in a clean room. So that will immediately follow Jens' class today, and going just one more step on the practical direction. Okay, so thank you very much, Jens, again, and see you everyone on Friday.
Stop recording.
Okay.